I've like done all my I just I have a horse show on Saturday and Sunday. I'm going home. Alan, my other cousins.
You lied to him? Yeah, I lied.
We call her Danny. No, it's not. She's Amanda.
All right, so for today, we have a group quiz at the end of class that covers the stuff we did last week. There is Mastering Due tonight, and there's Mastering Due Wednesday night, which covers Chapter 15, which you can do all right now. We're just going to do the one last topic that's in Chapter 15. And there are the optional science seminars, Tuesday and Thursday. So Tuesday's the biology one at 11 a.m., Thursday's the chemistry one at 11 a.m. If you find you can't attend any of these seminars, email me. I'll send you a video that you can watch and summarize as though you went to a regular seminar. So lots of options to build up the extra credit. All right, so last thing in Chapter 15 is talking about polyprotic acids. So polyprotic, like we talked about at the very beginning of the chapter, is an acid that's capable of donating more than one proton. So let's do some recapping first. If I'm going to talk about the acid equilibrium constant, and I say the Ka decreases, all right, the Ka decreases between two choices of acid. I have a Ka, I'll make these up. Let's see if I have a Ka of acid 1 of that, and Ka of acid 2 of which one of those two Kas is the stronger acid? 1 or 2? How do we know? What are we trying to get to? Right, you're trying to get the products. Is it easy to tell this way? It's a little tricky, right? What's the other way I could convert these numbers to make it maybe a little more obvious? Right, if I want to do the pKa of these, I made these numbers off the top of my head, so I have no idea what the answer is. Let's see here. 8.4, negative 4. All right, looking at the pKa's, which one is the stronger acid? The first one, right? Lower pKa, stronger acid. Or, if we look at this, bigger Ka. Both would be true, so. Okay, so a stronger acid has a larger Ka and or lower pKa, whichever way you want to think about it. I like pKa is better because they're kind of whole big numbers. Those are easier for me to think about. So when we talk about polyprotic acids, we're going to use the same logic to figure out the likelihood of each of these reactions happening. So let's say, for example, I have phosphoric acid. Which is H3PO4. So I could imagine this first reaction. What is one of the products that will be made from my phosphoric acid dissolving in water? Okay. Taking a little time to warm up today, that's all right. All right, so if I have H3O, if I have my hydronium, how many hydrogens do I have left on my phosphoric acid over here?
2.
Right, I have 2. And then what kind of charge does it have? -1. Okay. Does phosphoric acid in my new form over here have protons it can still donate? It does. Let's say that goes on to react. What would be one of the products? Still got that guy, good. And then how many protons are left on my phosphoric acid when it gets over here?
1.
And then what will its new charge be? -2, or 2 minus. Does it still have a proton it can donate?
Yes.
One more, all right. My aqueous are starting to look a little sad. All right, so using the same method, right? We have all 3 of those reactions. All right, so looking in my table of Kas, I could see that the Ka of H3PO4 is 7.5 times 10 to the -3rd. The Ka of H2PO4 minus is 6 times 10 to the -8th. And the Ka of HPO4 2 minus is 3.8 times 10 to the -13th. Those are really tiny. That's a 13. I ran out of space. All right, so looking at those 3 Kas, which one is the strongest acid? The first one, the second one, and the third one? All right, the first one's the strongest acid because it has the largest Ka. Right, so this is the strongest acid out of the 3 choices. Which one of the 3 is the strongest base? The first one, the second one, or the third one? Third one, right? Because it's the weakest acid, so it makes it the strongest base. So, as my Ka is decreasing from 1 to 2 to 3, it's telling me that it's harder to remove the proton, so it's less likely to make products. But what is this reaction down here? Is it more likely to get products or more likely to come back to reactants? Right, so if this is saying that the Ka, this guy is actually a weak acid but a super strong base, it is more likely to gain a proton than it is to give it away. So this third reaction's not particularly likely to happen. It's an option, but just not likely, right? As we're looking at equilibrium constants to -13, pretty tiny. All right, keep that in mind. We're going to use it in our next chapter here. Any questions about chapter 15 before I move on? Yeah, Rachel.
So it's correct to say that stronger bases have a smaller Ka and or a higher pKa?
Yeah, yeah. Okay. other questions about chapter 15, just plain old acids and bases? Well, in that case, let's talk about how we can get acids and bases to do work for us by looking at buffers for starters. So, a buffer solution is something that resists a change in pH when you add a small amount of acid or base to it. Alright, so many people have taken like a biology lab or a animal science lab where you use a solution that says on it buffer pH something something. Well, something to look forward to. Yeah, you will all, yeah, chemistry classes have buffers, so lots of buffer solutions in science. So we're going to talk about how do you make them and why do you want them. So a buffer I'll write the sentence instead. So a buffer contains a conjugate acid-base pair. And the reason I have the conjugate acid and base pair is so that when you add either an acid or a base, the opposite neutralizes it. So So if we add acid to our buffer solution, the base in there will neutralize it. If I add base, it will be neutralized by the acid. So how does this work out practically? So two common buffers we're going to talk about a lot are going to be phosphate buffer and acetic acid buffer. So let's look at phosphate buffer first. So just like we had in the previous, like one slide ago. Let's say I have this version of the phosphate ion, the dihydrogen phosphate. And if that's going to act as the acid, what would be its conjugate base pair? Right, so I'd need to have both of them in there. And if I have both of them, if I add acid to a solution that has both of these, the base will abstract the proton from the acid and turn into the conjugate acid. Or if I put base in there, the base will react with this and turn it into its conjugate. So you're not producing a new species, you're just changing the ratio between the conjugates in the solution. All right, let's say I have acetic. All right, so if that's acetic acid, that's my acid in this case. How many protons does acetic acid lose? Just one, right? So what's its new charge? Okay. So if I add some OH minuses to the solution of the acetic acid acetate ion, the acid becomes the acetate ion, and the base was the OH I added, neutralized. So if you have your calculator, go ahead and fish it out. We're going to start proving this mathematically as to what happens. All right, so for starters, what we'll do, let's look at a problem that I just want to make a buffer. So this problem is just a making the buffer question. We're not going to do anything crazy to it. We're not going to add anything to it. We just have our two components, and I want to know if I add those two things together, what's going to be my pH of that solution. So what is the pH of a buffer solution that contains 2.2 grams of ammonium chloride and 250 milliliters of 0.12 molar ammonia? So where this is going to be different from what we've done before is now I have two things in my solution at the initial. All right, so all the other ice charts we've done up to now had only one component. Now we have two components. So what do I need to do in order to use an ice chart? What kind of solution do I need to be in? Right, I need to be in concentrations. I need to be in molarity. I am not in molarity yet. So how do I figure out the molarity of this guy? What piece of information have I not given you yet? Molar mass. Okay. All right, everybody take a second and figure out the molarity if I have 2.2 grams of that and 250 milliliters. Everybody get something ballpark like that, 0.16. No one's saying no. Okay, good. All right, so now I'm in molarities. What is the next step before I can make my ice chart? Right, we need a balanced equation. All right, so let me ask this question first. Is the conjugate acid reacting with its conjugate base? I have a solution of the two components. Are they reacting together, or are they on opposite sides of the arrow, interconverting? Option 1, reacting together. Option 2, converting between the two choices. So the reason I set up a buffer is so that I can convert, right? If I add base, this one makes this, or that one makes that. So they're not making a reaction together. They're going to be on opposite sides of my arrow, right? Every time we've done a conjugate base pair, it's been on opposite sides of the arrow. Still true. Conjugate acid-base pairs have to be on opposite sides of my equilibrium arrow. So, it means I have this guy right here. And if it's not reacting with its conjugate base pair, what is it going to react with? Right, just plain water. And if I set it up like that, that's the acid, that acts as the base, then I have this as the base. And that is my, yeah, Rachel.
What happened to the?
It's just a spectator. It's just floating around in there. You could add it to both sides, but it would cancel out. All right, so my mass balanced in my balanced equation. My mass balanced. Yes. Am I charge balanced? Yes, right? So I got my mass balance, charge balance. Okay, so now we are ready to set up a nice chart. I understand Mondays. We have to stretch it out here in a second. Get blood flow going back to your brain. All right, so now I'm ready to set up my ice chart. All right, water's just our regular guy, like always. How much initial ammonium do I have? All right, that's the number we just calculated. How much initial ammonia, no, this is ammonium, ammonia. How much ammonia do we have? Right? One, two. How much initial of this do I have? Right, as far as we know, 0. So, we're going to do the same thing, right? We're going to lose 1x, we're going to gain an x, So at equilibrium, we're at this. So now we're ready to write, do I want to write a Ka expression or a Kb expression? What's my original reactant? An acid we're going to write as a Ka.
How do you determine that again?
Because it's the acid is the reactant. If I wanted to flip it over, right? Because it's reactants over products. Products over reactants. To be an acid, the acid has to be on the base, on the bottom. All right, now I go to my book and I would look up the Ka of NH4 plus. Right, so that looks pretty awful, actually. What can we do to simplify my solving for x?
NH4+ is a weak acid, so
Right, so both, I have a weak acid and a weak base. So my minus x will be small and my plus x will be small. So I can state with fairly good confidence no, that's way easier. Everybody calculate along, make sure I'm doing this right. We're just going to eyeball it. Is x much smaller than 0.16? Right? X is much, much smaller than 0.16. So did I make a good assumption? Yeah, I made a really good assumption. Okay, good. Right? I mean, you could calculate it out. It's definitely less than 5%. So how do I get from, you can't see what I just underlined, how do I get from what I just figured out, x, to pH? Because what is x? Right, it's this guy. Right, that's my hydronium, which is what I need for pH. What would we expect this pH to be? Do we have any way of guessing? we don't have a real great way of guessing because we have initial amounts of both and we have a little bit acid made. And so these are harder to predict if your pH is spot on. So you're going to have to be more careful with your math for these. So like in some of the previous examples, we knew that we were only putting in one component, so we can make a prediction about the pH. Here we have two components. It's a little harder to predict exactly what the pH should be.
So is this that's a specific characteristic of like making a buffer?
Is what a specific characteristic?
Like, there being like 0.12 on the product side.
Yeah, so all buffers will have two initial components. Yep. All right, how do we feel about that? Okay, we feel okay. Let's see. All right. Let's talk about some general things about buffers, and then we'll come back and we'll do a bunch more problems. All right, so the problem we just did, we found the H3O plus, right, the hydronium concentration by solving this equation. Right, that's what we just had in the previous equation, which we had as, right, it was x times 0.12 over 0.16. Well, we wanted the hydroniums by themselves, so rather than having x over here and doing the extra math to move it around, we can rearrange the equation so we obtain a very useful version of the equation. I can rearrange it because, right, I wanted this by itself. Oh. Now I have my hydroniums. It's just a ratio of my conjugate acid-base molarities multiplied by the acid equilibrium constant. All right, so my H3O plus is equal to the ratio of the conjugate acid-base pair times Ka. Turns out that's true for all buffer solutions. So that's handy, all right? It's handy to have a way of saying, well, just about always these problems are asking for the pH And so if there's a way to like plug in the information and get the pH, get the hydroniums out every single time without doing a lot of rearranging, that would be helpful. Super useful. Well, wouldn't it be even more useful if I could skip right ahead to the pH? Yes, it would be. I ran out of space. Fascinating math facts continued right here. All right, so let me flip over here, right? So I have it in terms of H3O plus and Ka. How do I get this guy into pH? What happens to this guy?
It goes to PK.
He becomes the pKa. So let's go ahead and do that. So now I have pH. Yes, plus negative log. Because on the previous equation, it was a plus, well, it was a times Ka, which then makes it a plus. Logs are weird. So then we do this. And I don't like that negative log, so I'm just going to write it out like this. Negative log of that is tricky, so we're just going to do. So we now have a way of getting pH directly from the pKa times the log of the conjugate acid-base ratio, which I've boxed it because this is one of my favorite equations. This is the Henderson-Hasselbalch equation. Not anything to do with the football player, just happens to have the same sort of last name. So, because that's a long name, I'm usually going to abbreviate it, the HH equation. This is going to be the go-to equation, pretty much in most of biology, all of biochem, is a lot. So, go ahead and box that. All right, let me tell you one or two things about it, and then I'll make sure we have enough time to do the quiz. All right. So this Henderson-Hasselbalch equation the equation shows that the pH of my buffer is controlled by two important factors. One, strength of the acid, right? Either the Ka or the pKa. That tells me how strong the acid is, and it's included in the equation, so that's a big part. The other big part is the conjugate acid-base pair, the two species ratio. So, if we are looking at, if I zoom in at just the ratio of A minus over HA, when I use those brackets, what am I actually saying in terms of units? Right, molarity, which is moles per volume. Right, moles per volume over moles per volume. If I make a solution that has both the conjugate acid and base in it, what is true about the volumes? They're additive. Would the volume on top and bottom be equal? Yes, right? Because I pour both of them into a 250 milliliter flask or 500 milliliter flask, but the volumes are equal, which means they cancel. Which means really this is a mole ratio of conjugate base and acid. What if I had an equal amount of moles of acid and base? It would be 1. Then I would have right, that would be true. If I now plug that into my equation, I now say this is 1. What's the log of 1? 0. The pH equals the pKa if this is true. How handy is that? If you know the pKa of an acid and you put in equal mole ratios, you already know the pH. Done. Super handy.
That's only if you have the same amount.
If you have the exact same moles. So last thing we're going to say about the Henderson-Hasselbalch equation before Wednesday is when we have done all the ice charts up to this point, what were the units in our ice chart? Molarity. We're now going to talk about mole ratios. Our new ice charts for the rest of this chapter will be in moles. So we're going to use moles ice charts. So start thinking in your head, if it's just a pH question, molarity. It's a buffer question, moles. So, just because I want to confuse you. All right. You guys get in your groups. Make sure at least one person in your group has a calculator.